Okay. So now we continue with the discussion of the research, design, and data management, going on to Lecture 4. So this is Module 2, Lecture 4. And we go back to this continuum that we had talked about earlier. Let me set my arrow here. Of 0 linkage to 100% linkage. So this is familiar to us. So we have to rule out coincidence, the 0 linkage, the spurious association, as we know, and an expected outcome is highly unlikely. So there's 0 predictivity at this level. We can establish an association, plausible or possible at one level. Correlation, of course, here's where we rule out chance. So we go from spurious association to chance association. This is where the statistics comes into play. And then correlation is still basically statistical or mathematical approaches to strengthening the association between the test factor and the outcome, the data sets that we have. And then, of course, finally is to establish causality, the 100% linkage, certain and totally predictable, that the test factor is directly affecting the outcome measure. So we have the, whenever we see differences between groups under study, there are these 3 possible explanations. We begin, even though we'll talk about each of these, we begin with spurious association because this is where we have to deal with the variation. If we don't have tightly controlled studies such that the only source of variation, the only 2 sources of variation are that caused by nature, the natural variation, and that caused by your test factor, so that you have variations from one treatment group to another when you analyze the data across those samples. There will be variation, and then ultimately the source of that variation is that this treatment caused the data to look differently than in the control group. So this is where we're headed. Let's make sure we've got good, reliable data, talk about ruling out chance, the statistical approaches, and then how do we establish causality. So we first must rule out spurious association and chance, progress to strengthen the association between the test factor and the outcome, and we'll talk about these as we go along. So spurious association is true artifact. It can be caused by non-comparability of your experimental groups or inequality of the groups. This means that the experimental design is flawed, and there is the assumption that groups are alike in every respect except the defining characteristic, this test factor that I mentioned. So we're going to be thinking about our independent variable as the variable that we can manipulate as the researcher. It's our test factor. We change that, and then we measure some outcome, and of course that's our observation. So there's test factor and outcome measure that we talk about. So the only difference between our treatment groups should be the test factor, either absent or present at differing degrees. So the groups are treated alike in all the procedures, so same time of day, all those types of things that we're very familiar with, same temperature, same light-dark cycle if you're working with animals, for example. The group makeup is similar with respect to other test factors not under the study. So everything else in the environment of your observable individual unit, whatever it is, are strictly controlled. The spurious association has different factors affecting the estimates of the population sample, and this is the bias. So we're going to talk about 2 things, bias and confounding, and they're the major sources of variation other than natural variation that have to be controlled for. So this refers to a systematic error. So it's not natural error, it's not natural variation, it's not the experimental error, that term that we didn't like before, that was used for the natural variation or residual error, whatever it is. This is systematic error, the way that you approach it, the things that you do as a scientist. So there can be selection bias, and that occurs when the subjects selected for the study are not representative of the population from which they were chosen. Prime example of this can be in human studies, where the selection of the subjects is so restricted that when you collect the data, you can't apply it to the general population. A prime example historically is that almost all studies have been performed in males, and of course the extension of that to the human female population was just generally accepted, and it was erroneous. It was a selection bias for many, many generations of research. A prime example, some of the earliest tests of the cardioprotective effects of estrogen was performed in males. And of course it was abandoned because it produced gynecomastia, the development of breast tissue in males. So that was the end of those experiments long ago. And now went through a phase of believing that estrogen was cardioprotective, and now I think since then there's been another study to show that it may not be quite so cardioprotective. But anyway, it makes the point. There was a selection bias, and therefore you couldn't apply it freely across the populations. Another example is some of the antidepressants, the selective serotonin reuptake inhibitors, have always been tested in adult humans, not in pediatric humans, and therefore we've seen the recent discoveries of the increase in incidence of suicide in human pediatric patients that are treated with the SSRIs, primarily for individuals suffering from depression. So again, a selection bias. All of the data produced to get the approval through the FDA from adult human population, not in pediatric samples, and the drug and its use was not appropriate for pediatric populations. So the results cannot be applied to the broader population they're supposed to represent, and they cannot be generalized. So the second case, of course, is a much more significant one where humans are placed at risk, and that is, as we know, absolutely unacceptable in science and medicine. The other is misclassification or information bias, and this is resulting from the systematic defect or inaccuracy in the measuring device itself or in the observer obtaining or recording the measurement. This can be correctable. This, of course, is when we think of calibration of an instrument or training of the individuals making the measurements and the observations. If you use a common instrument and the people that were in there before were twisting knobs, you go in and just collect your data without making sure that it's calibrated, and your entire data set is going to be wrong, then you have a misclassification or an information source of bias generating variability in your data set. So let's take a look at this graphically. We're back to this frequency distribution. We represent the bell-shaped curve with the sample mean, and we remember that that is x bar and that the population mean is mu. So as I said, you do you take a sample of people's blood pressure on some new island, some new population of humans, and it's the systolic pressure is from your sample is 210, and of course you go looking at the actual population mean, and it should be closer to 120. Then you have a bias, a selection bias. There is something wrong in the way that you collected the data, or maybe you have I can never remember the name of this other one, a misclassification bias. Maybe someone didn't calibrate the sphygmomanometer. You're at a way up on the top of a mountain on this new tropical island or something, and for some reason you get much higher pressures and it's not an accurate reading. So what bias means is that the sample mean is not true to the population mean, that there is a difference. So therefore, when we are considering spurious association and bias, we can begin to talk about precision. So precision refers to the degree of chance or random error or variability in an estimate, your sample. The greater the variability, the less precise an estimate will be. For a continuous measurement, it follows that the greater the standard deviation, the less precise an estimate of the mean will actually be. So here it is illustratively. We can now work with our different bell-shaped curves. So here we've got one really tight to the center, and the variability therefore is low. Excuse me. And then in B, the dispersion is a little bit greater, so the standard deviation here is going to be very low. Standard deviation here is going to be higher, and even higher yet here in this sample shown below. So we have high precision here and lower precision as we proceed through this. So again, we can come to our illustrations on the document camera and envision our graphs. So we're going to have a bar graph, and let's say they all have the same mean, but the error bar on the first one is going to be really teeny tiny, a little bit bigger on the second one, and quite a bit bigger on the third one. Or if it's a line graph, we see the same thing. So we've got our 3 data points. Maybe they are different, and the error bar is going to be like this, a little bit bigger and much bigger on the third one. So this is what I want us to be doing, is in our mind be picturing data like this, going back to the images here, I'm pointing over there, and be able to say that when I've got a bar or a point on a line graph that has a large standard error of the mean on it, then there's variability in that data set. That data set is not very precise. What is the source of that variation? Is it bias? So these are the questions you have to ask yourself, and the questions you want to ask anyone else when they're presenting research data or proposing a study with pilot data. So again, if we pictured all of these graphed, say the means, we were thinking that the means actually might be different for all 3 of these. So in the case like this where the means are different, so we've got our whole distribution of data, and we're going to have the 3 curves. We've got the nice tight one here. We've got the other one that's a little bit wider. Then we've got the third one that is like this. So the means might actually be set apart from each other significantly. That's not really a nice bell shape, but I think you see what I'm saying, is that we've got this area of concern here, overlap of data points, and then this area of overlap of data points. Your statistical test is not going to say that these are 3 different samples representing 3 different populations of data sets. You're going to have too much variation in one of them or more than one of the groups, and you're just not going to have a significant difference when you get to the end point of your statistical analysis. So this is the value of thinking of the data like this, but more from the perspective of just doing a bar graph or a line graph of our data, whatever is appropriate. Get it on paper, take a look at it, and look at our error bars. If you've got high error bars, you've got a source of variability. It's not a precise measurement. You've got to hunt it down and refine it. Otherwise, you're wasting your time continuing to collect data. There's something wrong with an instrument. There's something wrong with the sample that you're taking. So that's what that means. So we have now a formula where accuracy equals precision minus the bias. So we talked about bias. It is, of course, the difference between our sample population and our sample mean and the population mean. So the closer those are to identity, then the better measure we have. We have eliminated bias. Our sample is truly representing the population. We control all of our sources of variation. We control precision. Then we have the greatest accuracy in our measurement. We'll look at these graphically in a moment. So of a sample estimate such as the mean, which we're using for our normal population, refers to how close that estimate is to the true value in the population from which the sample was obtained, and also with similar dispersion around the central tendency. So if a measurement process is free of bias, it is accurate. Now there's something to be careful about, and part of the skill that we're developing too is that if we see somebody's data set and there's nice differences between the means and the error bars on every measurement are really, really tight, then we begin to ask the question as to whether the data is truly valid. Has somebody been tampering with something to make this data look far too perfect? It can be real, but the tighter the data, the more precise the measurements to where there's very little error, very little variation, then the more questionable that data is. It just doesn't seem real to have error bars in every measure so tight. Doesn't mean you can't have them, but it should be a warning sign if you see it. So let's ask ourselves the questions here to kind of test our abilities now. Here we have the sample mean, and we have the population mean, and there is a bias. And then here we have the sample mean and the variability for that sample mean. So this is a biased but precise estimate. So you're getting really good data points, but they mean nothing because you're never going to be able to relate them back to the sample population. So you probably have some type of sampling bias, misclassification. No, it's not. Why can't I not ever remember these darn things? A selection bias, but you may have good control over the potential misclassification biases. So your population mean is not being adequately represented. And then this is a sample mean and the population mean that are overlapping, but you've got a high degree of variability. So this would be less, also not quite as accurate, where you'd have a high precision, a low bias and a high precision. No. The high degree of variability is low precision. Okay, so hopefully you're correcting me all throughout there. So this is not very precise, but there is very little bias. So it's an unbiased but imprecise estimate of the population. So you've got some source of error that you have to be able to identify. So continuing on then with this discussion of bias, the non-comparability can be the selection bias. So you have to work on the selection of the subjects. How are the samples taken? You have to be careful about dropout. So if many of your subjects or your samples are lost, then you have to question the quality of the data points that you would be receiving. You might get a high level of bias, or it may also, of course, contribute to variability because of in our work, of course, we often have to repeat the sampling. The misclassification, the measurements on the study characteristics. So as well from, say you're using an instrument where it isn't calibrated for all of your studies and your entire data set is going to be biased. It's not going to represent the true population. But if it is not set correctly each time you go to use it, you measure some samples today, measure some samples tomorrow, before and after lunch, whatever, and if it's set differently each time, then you're going to have an imprecise measurement when you put all those numbers together. So this is the way that we're beginning to think about bias, separating our sample mean from population mean, but also the same sources of bias on an irregular basis contributing to the variability. And then confound bias is another, and that is the makeup of the groups. So the identifying and quantifying sources of bias and variability are what we can consider next. So we identify the factors that might affect experimental outcomes. So what is the target population? So if you don't know the population that you're going to try to extrapolate to or generalize to, then you're going to have obviously problems with your bias there. So how will a sample be selected from that population? What are the experimental processes and procedures to be performed in the course of the study? In other words, the subjects utilized should mimic the target population to the most reasonable extent possible, and the sample must be related to the study objectives. So these are quite obvious, but we're just running through them. So, for example, the design study to be conducted in animals, you specify the species, the strain, the age range, the weight range, the gender, and any other characteristics that make the study a realistic representation of the population to which you wish to apply it. So you've got to be able to fit it back into that theoretical framework. So what are some of the potential sources for bias? So the allocation of experimental units to the treatment conditions. So if you're very carefully selecting, well, these will be in the control and these will be in the treated groups based upon some characteristics that are going to favor the data that you're going to collect, then that obviously is going to produce a bias that is unacceptable. The protocol for the measurements taken has to be tightly controlled, or you'll have the bias as we had indicated. Using the wrong concentration of chemicals or a variety of things such as that. Association between unwanted variables and treatment conditions. So have to identify all the possible variables that you must be able to control, keep them all controlled from one time to another. Other experimental design factors of interest are potential sources of bias as well. So what are the primary methods to minimize these? Obviously, randomization of the allocation. We all know that we need to take a random sample and assign our source of experimental units randomly to the different treatment groups, different approaches to doing this, blinding of the subjects and the investigators to the treatment conditions. So I challenge anyone who's doing experiment at the bench as to whether you truly are blinded to your experiment. If you use a chemical or a drug, do you know what they are when you apply them to your experimental units? So does somebody else prepare them for you, or do you prepare them and have them labeled? Somebody goes into the room and covers that label so that when you go and retrieve them, you don't know which is which. So you're completely blinded to the study. You never know the treatment of any one individual unit when you're collecting data on it. So you can't accumulate the bias as you're collecting the data point. So if you don't, if you do know any of the treatments for any of the studies you're doing, then you have a bias, and many individuals in science believe that if you are not blinded to your experiments when you're performing them, then the data is invalid. It's very frustrating doing a true blinded study. We typically hear it for human studies, double-blinded, where the observer and the subject don't know what their treatment group is, but it applies to us at the bench as well. If I'm doing my study, making my measurements, now I'm going to add the test chemical, the test factor that's going to be the independent variable, and it's going to change my dependent variable in the way that I think it's going to. You're sitting there waiting for the data to look the way you want it to look. There can be confounding variables that must be determined before the experiment, so you've got to identify as much as you can before the experiment. Examine the properties of the assays to show accuracy, precision, sensitivity, specificity, and reproducibility. So these are extremely important. You have to be able to reproduce what others have been able to produce with your method, and demonstrate all of these before you begin collecting data. So obviously pilot studies are extremely important. So you've got to identify and quantify potential sources of variability, or the failure to test the biological process of interest. You might be going about it entirely wrong. To determine the intersubject variability within subject variability, so if there's subsampling by biological unit within the subject, such as the cells, then you make measurements day. Something might be different on the measurement day, the day of the assay, the laboratory instrument used, technician, source of reagents. So all of these things are potential sources of bias, the misclassification bias, and can introduce variation and make your measurements imprecise. Mainly to identify which of all possible factors contribute most to the variability. So what is the source of variability? So then we control them in a variety of ways. There's two approaches to eliminate the potential biases. You have all the assays for a given study performed by only one of the technical persons, if this is a feasible workload. Can't always be done that way, but that would be ideal. Somebody is the expert with that technique, and they're the only ones that do it. To split the assays equally between technicians and do this in such a way that the treatment conditions are also equally balanced for each one. So some way of smoothing it over, but still trying to minimize the source of variation in the data, or the potential introduction of bias from one measurement to the next. For the selection bias, obviously, you choose all subjects from the same population, and they should differ only in the test factor. Use randomization of assigning them to the test group, and then to complete the follow-up on dropout outcomes. Collect as much data off all of your original selections in your sample population, and include them in the analyses up to the point where you might have to exclude them. If you're doing a 10-day study and you only get 3 days out of one of them, keep them in there to do a preliminary evaluation, but ultimately you're probably going to have to exclude it, and that would be reasonable. For the misclassification bias, blind the observers. It can make a big difference. Define the criteria for outcome assessment. This ensures the consistency and the comparability. Have everything set up beforehand on how you're actually going to acquire your data and make your measurements. What is the standard protocol for calibrating instruments, and time frames for completing measurements, and a variety of things like that. You can't do things one way one day, incubate only an hour today and 2 hours tomorrow. Obviously, these are not going to be consistent approaches, and you're going to have misclassification bias. And if that bias is different from run to run of your procedure, you're going to reduce precision as well. You have to use control studies. So how many and exactly which ones can be challenging, but you should have as many as are feasible, and have one just from the general population. So this naive control group can can really be considered as essential, even though sometimes it might be a bit awkward to work with it. It still is essential. Can you just randomly sample from your group and get values that represent the normal, unperturbed group in the population? So you use these control studies to determine the risk for natural variation and try to manage all the environmental controls that you can, and use the double-blinded approach whenever that is possible. So if you're collecting data points, you're blinded when you're doing it. You don't know what the chemicals are that you're adding, or the manipulations are if you're changing temperature or whatever it is. You don't know exactly which one it is and what potential outcome is expected to be. If the data is collected and then sent to someone else to work with it, they don't know what the treatments are either. They just get the coding to put them in groups and calculate the mean and standard deviation for each of the groups without knowing what the treatments were per group, just how they're grouped together, and then finally present that data and then decode in the end. That's one way of having a double-blind study. So nobody's looking at the information coming in and being processed until the very end, knowing what the treatments were. It's very difficult to do, but it is the ideal way of doing it to be able to look somebody in the eye and say, I controlled that aspect of misclassification bias. There is no chance of that type of misclassification bias being in my study. If you know every treatment that you did and you knew all the data when you were working with it, you can't make that statement. You can't look someone in the eye and say, there is no misclassification bias of that nature in my data. There's no way of proving it. So after the fact, what can you do? If it's there or not there, after the fact, you just have to live with it, and it may be discounting of the data, discrediting the data, and so on, invalidating the data, and that's pretty frustrating. So you have to demonstrate the measures of bias detection and control precede the test experiments. This is the notebook. This is doing the pilot studies, taking notes, recording strategies for eliminating potential sources of bias and confound. If not, bias cannot be ruled out. So if you don't have documentation of the approaches, if you don't do it, it can't be ruled out, then you are obviously in trouble. So the confounding can work in two ways. It can create an apparent difference between groups when one does not exist, and we'll consider this in statistics as well, or it can mask a real difference. So you can have so much variation that you really can't see the difference, or you can get a difference that isn't real. The two possible sources of confounding are bias in the selection of subjects, or chance, the change in the baseline characteristics. If you get a shift in baseline throughout your study, it is a horrible thing to have happen, and it's very difficult to deal with. So the approaches to eliminate confounding can be either in the design or in the analysis, so beforehand or after. So in the design, it would be restriction, so limiting the characteristics of the subject's eligibility for the study. We know about this. The problem is that it limits the generalization to the population, but there can be real cutoffs. If you establish your criteria before you start, and examples when we do experiments in anesthetized animals to measure blood pressure, and it was always the standard. If the resting blood pressure, the mean blood pressure, is below 90 millimeters of mercury, don't even complete the experiment because your data is going to be useless. Of course, the students would always complete the study, and then they'd have these data points that were way out there, and we'd have to get rid of them anyway, but they were never supposed to collect the data because we were trying to implement restriction in the design to exclude the data before it even is recorded. Matching the subject characteristics, one group to another based on more than one characteristic. Sometimes if there's more than two factors that you're testing, that can be difficult, but it should be attempted. Obviously, the randomization, stratification, so rank ordering characteristics first, then randomly assigning. Maybe you've got an age group or gender groups and things like that, whatever this may be. In the analysis, so the data analysis phase, so again, we're thinking about excluding data points before we even collect them, because they're going to introduce confounding, increase the variability. We're determining how to filter at the front end. And it isn't as simple as saying, if I don't like the data point, I'm just going to throw it out. You've got to have established criteria and work it out. In the analysis, you still can remove data points, but it is highly structured. So stratification, you rank order the outcome measures within and between groups, do a weighted average of the differences in groups across the strata. So this is a possibility. Use regression analysis or mathematical modeling. These control the effect of many confounding variables at once. Not very easy to do, but can be done. Gives adjusted estimate of the differences between the treatment groups and can determine the statistical significance. And we also have validity and reliability. What I'm going to do is stop there because we're out of the scheduled class time, and I'll complete this part of the discussion as a separate recording that will be posted. Appreciate your time and attention, and hope you have a wonderful day.